Hello and welcome back. Now with 20% more space and 40% more engine. Where we left off, we were outside of the Milky Way. There's a warm oceania with life, which I think that was the planet we visited last time, judging by its location. Now then, let's head off. Let's go to the small Magellanic Cloud because I haven't gone there yet, I don't think. I went to the large one. Who knows? That's the joy of the series. I just go to random ass places. Nebular or Nebulicer Minor. Nice. All right. Now then, the small Magellanic Cloud, like the large Magellanic Cloud, is a satellite galaxy of our own, or a proto-galaxy, a dwarf galaxy. A lot of fun stuff going on here. It can only be seen from the southern hemisphere, which kind of sucks. I like the Magellanic Clouds. Whoa, okay. Start looking for planets now. A white main sequence binary with 10 planets. Could be interesting. Let's go. Da 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 da. Yeah, I have absolutely nothing going on tonight, so I'm probably just gonna make videos and draw and make more videos. Yeah, that's probably it. I have markers on. I forgot to turn those off. Oh, there we go. Right then. They have two. Let's check the planets. Wait, what on here? Around the first star. What is this? A hot ice giant. That's a little contradictory, don't you think? At that close range, it wouldn't be an ice giant. It would be a gas giant. You only get ice giants farther out in the outer reaches of systems where you have the ice is condensed. Like in our system, we have. Let's go to that warm gas giant. Has moons. Let's go to the moons actually. But yeah, it's like in our solar system, you have Uranus and Neptune, which are cold ice giants, and they're outside past the orbit of Saturn, where you get those kind of formations. Where you have close range, you can get gas giants because they're warm enough. And well, actually, to be fair, Jupiter produces more energy than it actually absorbs from the sun, but still. All right, blue. Kind of a yeah, it's a little compressed. Right, it must be orbiting or must be rotating pretty fast. Let's find out. Orbital period 11 hours. Yep. Yeah, most large gas giants actually do bulge around the equator because of the fast rotation. Oh, there's a moon right there. And I say, let's go to it. No, warm desert. Is that the moon? Yeah, it's the moon. Let's do it. Let's do it. Ah, there we go. Turn the pointer off. Oops. I like warm deserts. Could be fun. All right, what have we here? Does it have an atmosphere? Oh, it has a tenuous one, but it's certainly there. Ah, there we go. It has a magnetic field because I see auroras around the pole, but they're not that. No, actually, it's comparable, I guess. A large basin there, probably from an impact. And is that cloud cover or is that just like silicates? And one way to find out. Boom. Let's land on it, shall we? God, I haven't played this in a long time. I need to like actually get back doing this more often. Because again, I'm just gonna keep. Whoa, those are clouds. It has kind of a Venus thing going on, just with a thin atmosphere. Let's see if I can actually like speed up. All right. Wow, this is an interesting little planet or moon. Go to those mountains over there. Do, 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 do. Well, pretty sure there's no oxygen in this planet's atmosphere, judging by the color scheme, but that could also just be because of silicates. Is that the star? Oh, those are other moons. Where's the sun from here? Oh wow, it's disorienting. But no, I think. Oh, there's the sun. Judging by the color scheme on the surface, I'm colorblind, but it's only shades. Give me a break. Let's see here. I'm seeing white, kind of reddy oranges, and yellows. Kind of a cream color, actually. Yeah. So one could surmise that there's actually a lot of reddish colors, a lot of brown and reds. So, especially in the atmosphere, so one could surmise that this thin atmosphere consists of organic compounds, as well as probably just dust. Some of the reds could be oxides in the dust. The definitely silicates, just by the color scheme and the planet's general look. Hard to tell, hard to tell. But judging by the clouds, it looks like there's organic compounds in it. Like with Venus's atmosphere, you have organic compounds, which are, well, sulfides and stuff, but well, like sulfuric acid and whatnot. Interesting place nonetheless. It's a desert. Apparent size, phase magnitude. What is its mass? It's a little smaller than Earth, but pretty close. Temperature is not too bad at all. Well, it's barren, that's for sure. Ooh, what's that? Hmm, interesting. Let's vacate it for now and go elsewhere. No point wasting all of our time on this moon. Because there actually are more moons here we can check out. Like that one. It's another warm desert. Let's go, actually. Maybe it's similar, maybe it's different. Who knows? That's the joy of the universe. It looks pretty similar. Actually, no, it has less of an atmosphere. It's similar in composition, however, its atmosphere is a lot thinner. Let's land those mountains there. Whoa, it's a lot more reds here. That better not be snow. Actually, I don't know. Let's see your temperature. You could have some frozen gases, I guess. But I wouldn't be too keen. Oh, wow. Okay, let's do this. Oh, yeah, look at these colors. Kind of reminds me of the painted desert on Earth. So one could surmise a lot more oxides, like which is the case for Mars, or it's just sand, various forms of silicate and kind of like shale. Oh, this is a cool. Oh, this is a crater. We're in a crater. Nice. I love the fractally generated terrain. But judging by the very thin atmosphere, I'm kind of curious about these ices. I'm gonna go on a limb here and say that the ice on these mountains is probably mostly dry ice, like condensed carbon dioxide, like with the Martian polar caps, which the actual white ice that you see is for the most part just dry ice, like frozen carbon dioxide from the atmosphere, because judging by the very thin atmosphere, you can't really have water ice because the pressure just makes it sublimate. It's yeah. It could be some water ice there. I'm not gonna put it against it, but wow. Look at look at this terrain. Whoa, some weird pressure lines or something. Let's back up and let it load in. Looking at how it's moving, it could be wind blown. Mm, it looks like something scraped along the surface. Actually, yeah, it looks like dunes, like something moved over the surface. Sandblasting water, I don't know. Interesting, I've never actually seen that before in this game yet. Cool, cool. Alright, where to now? What's this over here? An orange dwarf binary with 16 planets. That's an orange dwarf binary with one life planet. Let's go to there. Da 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 da. 10 minutes in. We're doing fantastic. Sorry about that. It's raining outside. It's kind of nice. I like rain. It's been a very wet summer. Not gonna lie. Doo -doo -doo. Orange dwarf spectral K5V. Alright. Warm Terra. The game's a little frozen. Let's give it a second. Ah, here's the warm. Oh, it's a cool Terra with life. Temperature 245. What's the atmosphere? 186. So far, I have yet to find a planet with life with a comparable atmosphere to ours. They seem to always have, like, crushing atmospheres. It's weird. But hey, if a genetic code can form in any given environment, you can get life. And the genetic code can form pretty easily from random events. Oh, that's a nice little. This is an interesting planet. Let's get a little closer to it. But yeah, like just through random chemical occurrences, especially during the formation of planets, you get all you need to form a genetic code or a simple genetic code. Like they were able to show that well, let's see here, like they were able to make a whole bunch of organic compounds and amino acids and proteins through just natural occurrences that happen in the atmosphere, especially on Titan, which is a good analog for an early planet. And they were actually able to make actual like base or no, what are they called? Wow, my brain always goes blank when I make videos. But wow, that's actually a very thick disk. But no, they were actually able to make uh, three of the four or five, I should say, um, DNA, the linking parts. I know what they're called. I work with them on occasion. What is? Well, not dang. Whatever. You know what I'm talking about. Someone in the comments will say it if I don't remember it later on. But, but yeah, they were able to make the basic blocks of DNA. Let's see here. Adenine, thymine, guanine, cytosine, and uracil. Those things. I always feel stupid when I forget the names of things. Oh well. Anyways, and they were able to form through processes which are normally found on planets, such as like geological activity around vents and stuff. So that's interesting because if you can get a basic like an RNA code, then you can get basic natural selection. Whoops, we are stuck in this planet's atmosphere. Actually, another thing they found that if you have like cell membranes, like phospholipid bilayers, you can actually like make them divide and reproduce just by shaking them. So it's like if you had a phospholipid bilayer and a simple RNA or genetic code, then just basically moving them would actually make them reproduce. And that's, a mechanism of evolution is reproduction. So they've found that like life itself can form pretty easily and like just from a chemical standpoint, if you have the right condition, life is basically it's gonna happen one way or the other. Just from a chemical standpoint, it's pretty cool. Binary planet, star, orange dwarf, 11 planets, 7 to binary. What's that? Orange dwarf binary, orange dwarf. Well, it's not a binary. Yellow dwarf. It's a G. Let's go there. I want to say base pairs. Like I'm going back to the DNA, a little piece. I know they're called base pairs, but I'm trying to think they have another name. Like adenine, thymine, guanine, cytosine, uracil. Because like in a DNA, like in a DNA strand, they're base pairs. I don't know. I'll check. I'll check when this video's done. Warm gas giant with only 3 moons. That's odd. Let's check it out, shall we? Yes, the constituent makeup of DNA. And of course, the double helix is just one variation. There could be other forms. What's this? It is a warm savanna, a hot desert. You're closest. What are you? It's a hot desert. It's actually kind of funny if you think about how DNA works at its most simple level. It basically, like all life is just, it all runs on electrical charges. Ooh, this is different. This is very different indeed. Has magnetic field, probably has a iron-rich core. That basin, a lot of impacts. Or are those craters? Yes, a lot of little impacts. Obviously been bombarded a lot. It has something condensed on its one of its poles. Some larger impact basins. Go back to the one basin over here. Let's land kind of on the Terminator. Yeah, because like a lot of people ask like how does DNA do what it does? And it's like if you just like look at it at its most basic level, it's just the atoms because it's like each base pair, like the little like let's say adenine for example, uh it has well not that many atoms in it. I think it's like around 40 or more than 40. I don't know. But it's like it all works because each base pair in relation to the other one has a specific charge to it because of the electrons in the atom and just the atom's charge itself. And when it's in a certain when you have all these atoms in a certain combination, such as a base pair, you the overall charge of that molecule is different. So, for example, messenger RNA, it works by you have a DNA strand which unwinds, revealing one half of the DNA. So you have all these different base pair things, and then you have the which is RNA, and each little like branch of the helix has a specific charge. And inside the environment of the nucleus, you have a whole bunch of pieces of base pairs and chemicals and stuff. And when you have this unwrapped like you have it unwrapped like so, then as you know the various molecules go by the open branches, you have some that will actually have the correct electronic charge and will actually bind to that particular segment of RNA. So, and this happens, and each piece, especially when you're making a protein, for example, in DNA, each piece has a specific molecule attached to the almost it's like a transporting protein, and as they bind to the RNA, the pieces on top actually combine to each other. So then once you have the entire RNA strand is binded together, um, they then release, and you have a formed strain, or you have a formed protein segment, and it just literally just formed by the charges of the atoms binding to each other, just so. So it's kind of like a puzzle where, you know, all these pieces fit in the proper location, and you put them in a box, and you shake the box, and each piece will bind to each other the way they're supposed to. So that's how DNA works, is it literally just binds with each other, various charges and all that. And that's how you make a messenger protein with messenger RNA going from the nucleolus to the nucleus to the actual cell. And yeah, that's how life works, is on its most basic level, is just electromagnetic charges in the atoms that make up the DNA. And when you kind of backwards engineer that, you can see how DNA works basically just by chemical processes and electrical charges. You can very easily see how DNA would actually form, or this early DNA could form randomly from just electrical charges in like some kind of chemical soup. And that's what makes the universe such a fascinating place is there's so many different variations and so many, ways for these chemicals to bind and combine and form possibly infinite variation of life. And it's like we're carbon-based because carbon is the basis of all of our DNA and our life processes because carbon is a subatomic core and will bind to everything and itself. But silicone can also bind with a lot of other things and itself, so you could potentially get a DNA strand or something similar based on silicone or what have you. It's just that currently organic chemistry seems to be the easiest to form, and there's a lot of organic compounds in the universe. I've even seen them form in on Titan's atmosphere, in comets. So it's a very interesting idea to go around in this game and look at these planets and just try to think. Although it's just a game, you can see what kind of stuff might be there by just by its chemical composition. Like this place is probably just a rock, maybe ferrous metals and silicates, like most other things. But still, you could, there's probably going to be organic compounds even on this rock, just from the formation, because organic compounds, especially carbon, is formed in stars and is released when it explodes or vents its layers. But we can talk about star life cycles in the next episode, which is also a fascinating topic. So yeah, uh, that's 21 minutes. I should probably end it here. I'll end looking at the galaxy. Thank you for watching. I hope you enjoyed, and I hope you got something from this. So yeah, space.